Okay, so we have finished talking about moment of inertia. Let's move on to the last subtopic, which is on conservation of angular momentum. Okay, conservation of angular momentum, it's a bit difficult to see how it fits to the whole picture, so I didn't really relate it to other stuff. But it's almost the same thing with chapter 3. It's analogous to linear momentum. So just now, if you relate the force to the torque, you use R cross F, then you become torque, right? Now you take R cross the linear momentum, you get the rotational momentum, which is angular momentum. Just like last time you use R cross F, then you get torque. This time you use R cross linear momentum, you get angular momentum. So what does all these symbols mean? L is the angular momentum of the particle. Okay, if you cannot think of any particle, I've drawn one particle here. The green thing is a particle. Then R is the perpendicular distance of the particle from the axis of rotation. Perpendicular distance means by, if you take this velocity direction, you extend the line in the direction of the velocity, then you find a particular point where you can draw a perpendicular line up to the axis of rotation. That distance is the perpendicular distance. Okay, so R is the perpendicular distance from the axis of rotation. P is linear momentum. If you change it, it's just mv. So the v is the linear velocity of that particle. So if an object, let's say this green point, if an object is moving like this with respect to the axis of rotation, even though it is not rotating, there is an angular momentum. Okay, there is an angular momentum even though the object is not rotating. As long as it's moving with respect to the axis of rotation, then you have angular momentum. Okay, but like just now, usually for a rigid body you have many particles. Then if you want to calculate this thing one by one, you take up infinitely long. So after some derivation and a lot of bim bam bam integration and stuff, you end up with this formula, which is angular momentum equals to moment of inertia times angular velocity. If you think of how this equation comes into place, you can see angular momentum, linear momentum. The angular or rotational mass, which we call in a moment of inertia, the linear mass or the normal mass. Angular velocity, linear velocity. So it's just the same thing, just that you change it to rotational form. This is for a rigid body. The I, you can refer to the many formula that I showed you just now in the previous video. The omega is just the angular velocity of the rigid body. Then what will come out is the angular momentum of the rigid body. Okay, so the first equation here is for particles, and the second equation here is for rigid body. They are related to each other, just that the relation requires integration, so I didn't explain it to you. Okay, so knowing angular momentum, we can talk about conservation of angular momentum, just like conservation of linear momentum in chapter 3. So what does it mean is the sum of the angular momentum at one point will be equals to the angular momentum at another point in time. So usually people, if there are multiple objects, what you can do is take the angular momentum of the first thing plus the angular momentum of the second thing, then equals to the final angular momentum of the first thing plus the final angular momentum of the second thing. But usually in your books, the formula is probably L1 is equals to L2. Therefore, I1 omega 1 is equals to I2 omega 2. Okay? This is if the object change its distribution of mass. Okay? Means by before that all the mass are near the center, near the axis of rotation, then you change the distribution, you push all the mass to the rim, you push it far away from the axis of rotation, you are changing the moment of inertia. So when you change the moment of inertia, reasonably the angular velocity will change also if the object change the distribution of mass. Okay, it's difficult to talk more about this, but probably I will create another video to talk more about conservation of angular momentum. So basically, it's just three formula: L equals to R cross mv, L equals to I omega, and for conservation of angular momentum, determine one event and determine one moment, determine the first moment, determine the second moment, sum up all the angular momentum for one moment equals to all the angular momentum at another moment. The moment here is moment in time, it's not moment of inertia. Moment in time means by a particular instantaneous, a particular instant. Okay, so that's conservation of momentum. So it's sort of like a standalone thing actually. So if you relate the whole thing together, what it means is if you have force being exerted at a distance, you have torque. Now, usually for an object, you have multiple forces exerted on an object. So if they're exerted at different points, what you can do is you use FBD, then you check whether the object, you draw FBD, then you check whether the object is moving or rotating or not. So there are two situations possible in our syllabus. One is when the object is not moving and not rotating. One is when the object is moving and rotating. So based on different situation, you apply different formula, just like case 1 and case 2 that I mentioned in the previous video. So if an object is not in equilibrium, you have angular acceleration because the thing is changing in angular velocity. If the angular velocity is constant, then you can use the four formulas, the four kinematic equations, if the angular acceleration is constant. Okay, since we talk about kinematics, let's move on and talk about other formula for kinematics. Only when you want to find the average value, then you are allowed to use this formula and this formula. But under very special situation where the omega or the alpha is uniform, the average value will be equal to the instantaneous value. So these are very specific situations. That's why this equation is not very oftenly used. Okay? So lastly, you have these four equations. These four equations, basically the usage is to relate a rigid body to a certain point on the rigid body. You relate the whole rigid body to a certain point on the rigid body. Okay, so these four equations. Then knowing what causes the thing, knowing what causes a thing to change in rotational motion, knowing how to describe rotational motions, we move on to talk a little bit about moment of inertia, because sum of torque is equals to I alpha. So for moment of inertia, you can compare it with mass to get an idea of how is it used. And for moment of inertia, you know it depends on first thing the mass, second thing the distribution of mass. So knowing that, you are able to construct this formula here. Then if that's the formula for many particles, you have rigid body, then there's a lot of particles, you cannot do it one by one. So scientists or mathematicians derive the formula for you, which you can refer to the table. Then next thing, you have a sort of standalone 8.4, conservation of angular momentum. Similar to linear momentum, you have, instead of P equals mv, you have L equals to Rmv. Okay, just like how you derive torque from force, you derive angular momentum from linear momentum. Then if you have many particles, just like a uniform rigid body, what you can do is you derive this formula. This formula cannot be derived, it requires integration. I mean, cannot be derived at your level. Okay, then knowing angular momentum, you can do something about the conservation of angular momentum. Conservation of angular momentum, well, it's a similar case for chapter 3. You find a specific instant, you find another instant, you sum up all the angular momentum at one instant, it equals to all the angular momentum at another instant. Okay, so for a very specific case where you can change the distribution of mass, and this is how the thing would change. You can change the distribution of mass. Okay, so that's it. That wraps up the whole chapter 8 overview. I'll probably do one or two videos to explain more of inertia or angular momentum in detail, but that's it for now. Chapter 8 overview. Thank you very much.